Hey, what's up, guys? So welcome to my third video about Galois theory. So previously, I introduced the algebra extension and separate. So basically, we have some terminology. One is the algebra extension, and the finite extension that I already introduced as a finite dimensional vector space. And if the order minimum polynomial has no multiple roots, this is called the separable extension. If you haven't seen my video, then I will post a link, the list below. And the first is the normal extension. So once you understand three of them, then you can give the precise statement of the Galois theory and the Galois group, and then you can use all this big machinery to dealing with the solving the polynomial equation and understand why the quintic polynomials do not have the one cannot use the plus or minus or take the square roots to get your solution. Okay, so separable extension, as I mentioned before, separable extension for the characteristic field of the zero is the same as the algebra extension. So separable extension is not difficult, right? So but the normal extension is the most difficult one. Yeah, I think it's the key ingredient in the Galois theory. Okay. So let's quickly start. Hope you guys subscribe to my channel. So definition, suppose you have a field extension is normal. Means that it's satisfied. Is satisfied. The first one is that L over K is algebraic. Right? This is somehow like every starting point. Okay. And the second is that for all L belongs to L, there's a minimum polynomial, right? P of X need to factors. So the minimum polynomial need to factors linearly in L. Okay, so this means that P of X can be written as X minus L and X minus L1. Okay, X minus L maybe N minus 1 in L. Okay, so this is called a normal extension. This is probably not easy to understand what this means. So let me just give one famous example. For example, you can consider the cube adjoint with the 3 square roots of 2. Okay, so this is the over cube, right? So this is not normal. Okay, the reason is that if you compute a minimum polynomial, right? So x is 3 square root of 2. So x cubed minus 2 is 0. This is a minimum polynomial. X squared minus 2 do not factor in the cube square root of 2, right? The reason is that it can only factor as x minus 3 square root of 2 and x minus 3 square root of 2 omega and x minus 3 square root of 2 omega squared, which omega is a minus 1 plus square root of 3i divided by 2, right? But this field do not have the imaginary. If you put into the complex number, right, there's no imaginary. So it cannot complete factor in the cube over 3 square root of 2. So this is called a non-normal extension. Okay, and simply maybe a trivial example is that this is a normal extension is that you take a square root of 2 and over q, right? So the minimum polynomial of square root of 2 x squared minus 2 equals 0, right? So this factor x minus square root of 2 x plus square root of 2. And then notice that the square root of minus square root of 2 is in q square root of 2. Okay. And this is very weird that actually in any cubic, I think in any quadratic extension, meaning that your solution satisfies the quadratic equation, it always becomes normal extension. Okay, but this is another case. This is a different the different thing I think is not important. Okay, so simple preposition. This preposition is simple. So let's say you have this and suppose L over K is normal. And you can easily check that L over M is normal. Okay, so remember that we already proved that if L over K is separable, then L over M is separable. And the least one is also trivial. Proof trivial. Okay. The reason is that the minimum polynomials already factoring out, right? So should factor linearly in M, right? Because the K of X polynomial can be viewed as a M of X polynomial. So this is proof is almost trivial. Okay. Okay. Now the most important one is this one. So this theorem is the key theory in the normal extension. Let's consider K over L is normal and finite. So finite extension means that L over K is a finite dimensional vector space. Finite. Remember, finite extension will automatically be algebraic. This is what I already proved in the previous video. Okay, and suppose somebody give you a finite extension such that finite intermediate extension. So this is finite. I think over over K. If it's finite over K, then it automatically becomes finite over M because LK is the same as L M MK. Okay, so you can easily check this. And every K, so given any intermediate field M, which is finite, and every K homomorphism, I will explain in detail later. K homomorphism from M to L. Basically, you can view it as a linear transformation, right? With two vector space and a coefficient K. This is called a K homomorphism from M to L. Extends to K automorphism of L. So basically, if somebody gives you F from M to L, right, there is an extension F tilde such that from L to L, which is automorphism. It's a K automorphism. So K automorphism means that F tilde is one-to-one onto and the homomorphism. And the K automorphism means that the F tilde of X equals X for all X belongs to K. Okay, so basically this normal extension is powerful such that if you have any intermediate field which map from the middle to the larger field, then you can extend it into a K automorphism from L to L. So this proof is a little bit tricky. So let me do it step by step. If you don't want to see this, then you can believe this is true. But I think this is the key point in the Galois theory. So hope you guys do not skip. All right, so you have a let's maybe do this. Let's relabel our intermediate field use N. So N is K and M L. Right. So I have this map. This is just the inclusion, and I have F right from N to L, and this is the same as L. This is K. This is the same. Okay. And I claim for every L belongs to L, then this F can be extended from N of adjoint L to L. Okay, so this is the proof technique that I don't prove this generally. I just prove it can be adjoined by taking L, put in an N, and then put in a simple. And once we prove this, then I can prove that once you can extend L, right? Because this is finite. So if you keep going, then you will finally terminate. So I mean, it's sufficient to prove this is true. Okay, so due to finiteness, this is already enough. Okay, so let's see. So if N is L, if I take original is L, then we are done. So I can assume that N is not L, right? So I can, let's say I choose L belongs to L, where L do not belong to N, and I can pick the minimum polynomial of L. Okay, and I know that by the way, I know this is finite. Okay. Okay, so now this is finite, right? So this is automatically algebraic. So I can find another Q of X. So now Q of X is a minimum polynomial of L, but in N, right? So over N of X. Okay, and then by the previous idea that I know that Q of X divides P of X. Okay. And P of X separated linearly, right? So decomposed linearly. So if you take F, right, you get F of Q of X divides F of P of X, right? So your F from N to L, right? So you can map all the coefficients from this. And then remember that F is a K homomorphism, right? So this guy will be P of X. So this guy factor linearly. So which tell you that F Q of X, right, factors linearly, right? Because this guy factors linearly, right? So it's subfield. It's subfactor. This is factor, right? Factors linearly in L. Okay, so yeah, the proof is done. Okay. Okay, the why the proof is done, right? Because now F Q of X factor linear in L, right? So if I take a L prime be a roots of this, so let's say L prime be a roots of F Q of X. So remember that originally your F contains this, right? And you can extend it into N of X, map to L of X, right? Just map any polynomial L of X to L of X. Okay, so now this F Q of X, right, factors linear in L, right? So which tell you that this F Q of X is an ideal of L of X generated by X minus L prime. Okay, remember that we have shown this. I have shown the result is that suppose you have this and you have a minimum polynomial of L belongs to L. A minimum polynomial L called P of X. Then one can easily see that if you add a joint with K of L, this will isomorphic to K of X quotient P of X. Right, so this is the same as this case, right? So which if you start from here, then you get an extension from N of L, which is isomorphic to N of X by this previous theorem, right? This Q of X, which extended to F tilde L of X quotient what? Because this F of Q of X factor linear in L, right? So this is just X minus L prime, and then this is just L, right? Because L prime belongs to L, because it factor linearly, right? So this is the key why we use a normal extension, right? Otherwise, this guy may have the multiple, like the square or something. So this will be the larger field. But I already say that it's factor linearly. So L of X quotient X minus L prime still be L. Okay, so yeah, so now we prove the answer. We will prove the theorem, right? Because we already say, and I already say that F can be extended from N of L to L, which is a K homomorphism. So you can keep extending, right? Finally become a K automorphism. Okay, so this is the proof. Okay, so the preposition. So this is the final preposition that I want to say. Okay, so if K belongs to L is normal and finite, the following are equivalent. The first one is that L1 and L2 are conjugate in K. So this means that L1 and L2 have let's say L1 and L2 both belongs to L, are conjugate means that they have the same minimum polynomial. And the second is that there exists F from L to L, which is an automorphism, K automorphism, such that FL1 is L2. Okay, so they can permute. Basically, you have a K automorphism which you can permute the roots. Okay, so give the proof. So which one is a simple one? It's a simpler one. Okay, so obviously the second to one is a simpler one, right? So okay, the why is the simpler one? Because now if I have L1, right? I have L1, then I have a minimum polynomial P of X, and since it's in K of X, and since F is automorphism, K automorphism, so F P of X will be P F of X, right? So means that now F P of L1 is the same as P F of L1, which is PL2, right? And this is 0 because P of L1 is 0. So which prove that L2 is also a root. And by automorphism, P of X is also a minimum polynomial of L2. Okay, so this direction is 2 to 1 is somehow trivial, right? Okay, so I think let's prove this one. So this one says that L2 are conjugate in K, then you need to construct this. Okay, so how do we do this? By the previous theorem, right? By the previous theorem. Previous theorem tell me that if I have any intermediate field M, which is finite, and this guy is normal finite, then any automorphism from K or K homomorphism from M to L can be extended. So now I know what I know that the K of X quotient P of X will isomorphic to KL1. There's a isomorphism, right? So there's a map from here, and I also know that there is a map from KL2, right? Because they have the same minimum polynomial, right? So that means I can create an isomorphism from KL1 to KL2. Okay. So, and the KL1 is a subfield. Is a subfield finite, and this also finite, right? So these are these are finite, right? And then these can map to this, right? So there is extension. There is an extension structure from L to L, and another extension from L2 from L to L, and then you just combine it. Okay, that's it. So there is a so basically you just need use the previous theorem that this KL1 will give you the extension. You just put it right. It will give you extension from L to L, and L2 also give you L to L, and obviously that you just compose with them. Okay, so now finally you get a K automorphism from L1 to L2. Okay, so that's it. So this is the normal extension. So next time we can talk about the Galois theory, and yeah, maybe let's. Okay, so let me just say something a little bit weird. So let me just say final remark. So usually so as I said, right, so Q of square root of 2 is isomorphic to Q of X, quotient X cubed minus 2. I think there's no doubt that this is true, right? But by the previous theorem that this guy should also isomorphic to Q of square root of 2 minus omega, times omega, right? So omega is this. So this means what? This means these are two isomorphisms, right? So these two are actually isomorphism because you just compose this. But these two are not the same field, right? Because there's no I here, right? So that means if you put them into the complex number, these are two different fields, right? These are two different fields. So there should be a map by this construction, right? If you extended L to be, let's say if you put L to be, let's say this is L, right? If we put L to be here, then there should be a Galois group. There should be some mapping. There should be some automorphism which you can map to 3 square root of 2 to this, right? So this is the Galois group. Okay. This is the element of Galois group. So basically, actually, yeah, I mean, let me say the Galois group in that. Okay, see you guys next video.